On battery modeling. Battery modeling is the concept of designing our own battery or choosing the battery which is now prevailing in the market. Because equation is widely accepted empirical relation among the capacity, discharge current, time, and many other specifications like specific power, specific energy, and time. It relates Q, I, T, S, P, S, E, and T. Ricketts' equation is used in developing the fractional depletion model (FDM) of the batteries. Two main forms of equations are prevailing in the market. The FDM can be developed using the constant current discharge approach or power density approach associated with two forms of the equation. Let's see the constant current discharge approach. So this is the model. For arriving at this particular mathematical model, consider the constant current discharge experiment. The battery is discharged under constant current conditions from 100% capacity until cutoff voltage is reached. The load resistance RL is varied to charge the constant current level and also to maintain the current constant for each experiment. The IV's data are used to fit Ricketts' equation with constant current. I is the constant discharge current, N are curve fitting constants with Ns with smaller current. Let's take an example of finding the current curve fitting constant and lambda for per equation. Then the current discharge experiment at the battery for T1, T0, I1 being 10 and 80, T2, I2 being 1 and 100. So here we need to compare the empirical form of the equation having a logarithmic function of the current and time to the logarithmic function of lambda. Rearranging, we can shape a straight line where the shape of the straight line is given by delta y by delta x. Substitution of delta y by delta x, we can write it in terms of log of time ratios to log of current ratios. That is going to give the n for the equation. Here we have considered lambda at two different values and n is supposed to be at 1.27. For that we have plotted a graph. So here this particular model is basically much more important to understand the working and modeling procedure for the battery. Who is the person who has coined this equation? It is always good to know a person who is behind this refrigerator invention where this equation is holding good in all the Purket's law presented by German scientist Wilhelm Purket in 1897, expressing approximately the change in capacity of rechargeable lead-acid batteries at a different rate of charges. As rate of discharge increases, the battery available capacity decreases, approximately according to Purket's law. Now let's relate it to the battery. Manufacturers specify the capacity of the battery at specified discharge rate. For an example, a battery might be 100 Ah when discharged at the rate that will fully discharge the battery in 20 hours. If discharged at a faster rate, the delivered capacity is less. The Burkett's law describes a power relationship between the discharge current and the delivered capacity. Over some specified range of discharge current, Burkett's constant K, the exponent, was equal to unity. The delivered capacity would be independent of the current. For real, the battery For real battery, the exponent is greater than unity and capacity decreases as discharge rate increases. First law of Burkett's is Cp I to the power k to t. Cp is the capacity at 1 ampere discharge rate, which must be expressed in ampere hour. I is the actual discharge current in amperes. T is the actual time to discharge the battery, which must be expressed in hours. K is the constant. The Burkett's law became a key issue in the battery electric vehicles where battery rated, for example, at 200 hours discharge time are used at much shorter discharge time for about 1 hour. At high load current, the internal resistance of the real battery dissipates significant power, reducing the power available to the load in addition to the grid reduction, delivering less capacity than a simple power law equation predicts. 2006, the critical study concluded that Burkett's equation could not be used to predict the state of discharge of the battery accurately unless it is discharged at a constant rate and a constant temperature. This law has its own limitation. The first one is the effect of temperature on the battery is not included in the equation. We do not say any current dependencies or any temperature dependencies in the equation. The battery age is not considered. The Burkett exponent increases with the battery age. Thirdly, if calculating for a low discharge rate, the equation does not account for the fact that each battery has a self-discharge rate. In terms of estimation, Burkett's law gets much closer to estimating real-world performance of the battery than simple exploration of ampere-hour rating. There are many research papers in this particular domain which basically gives you a much more insight. This law is concentrating on what happens is that the chemical process responsible for transporting active chemical around the battery progresses at finite rate. So, draining the battery quickly causes the voltage to reach the cutoff level prematurely before all the active materials in the battery is used up. Given time, the active material will diffuse through the cells and be available for further reaction. For example, if a battery with a capacity of 200 Ah is considered with C20 rate, then C20 means 20 hours rate of discharge. If the battery is discharged at 10 amps, it will last 20 hours, giving a rated capacity of 200 ampere hour. However, same battery discharged at 20 amps may last only for 5 hours. Therefore, it only delivers 100 Ah.